Already, I am concentrating most of my attention over there on the bottom left, right? Because I know my vertex is -5, -7, right? And then my y-intercept is the only other point I have is way down at -82, isn't it? So that means I better start counting. Let's count on our y-axis. Let's count by tens. -10, 20, 30, 40, 50, 60, 70, 80, okay, 90, way down there. -90. So -80. Now my x-axis, remember my x-axis doesn't have to be the same scale. So what was the x-intercept? It was -5, -7, right? So -5, why don't I just make this -5 right there? And that's -10. That fair? So here comes my vertex. I go to left 5 and down 7. Again, this is a ballpark. I'm just trying to get it close. -5, -7. It's my vertex. It opens down. And I only have one other point, right? That's the only one other point on this graph. And that's the y-intercept, which is way down here at -82. Again, just kind of ballparking it. So you kind of get a feel right now what this needs to look like. You know, it needs to kind of curve down like that. Now I need to make sure I don't draw a V. So sometimes what I do is I force myself to draw like a little U in here first, like that. That kind of forces the U to happen. And then I just go and as best I can get myself down to this one like that. And I think you can kind of see right now how that drawing that dotted axis of symmetry is sometimes helpful. That's not part of our graph, but that's sometimes helpful in drawing the other half. You can kind of measure things out a little bit. You can be like, all right, this is the distance from here to here. I can just kind of go over to the other side and draw a dot there. And if that's the distance from here to here, I can just go to the other side and draw a dot like that. Do y'all see what I'm doing? And if you do that, it just helps. It just helps it look better. And then like that. Okay. That's it. I mean, I guess you could label this point 0, -80. That's your y-intercept. So here is something kind of, I don't know if it's profound, but it's kind of interesting, I think. Here's a function, right? I could start giving you values right now to plug into this function, right? If I said, hey, everyone, plug in 1, you could plug in 1, right? And it would spit out an answer. I could say, plug in 10, you could spit out an answer. What is the largest answer that will ever come out of this thing? No matter what you plug in, what is the largest number that will come out? Look at your graph. Negative. -7 would be the largest value. See, look, when we talk about large, you have to think about number line. Look, if you have a number line, here's 0, here's 1, here's 2, here's 3, right? 3 is bigger than 2, right? 2 is bigger than 1. 1 is bigger than 0. 0 is bigger than -1. -1 is bigger than -2. -2 is bigger than -3. So when I say, hey, what's the largest value that could come out of this? I'm saying, what's the highest point on this graph? And what was the highest point? What was the y coordinate over here? It was -7, wasn't it? It's that y coordinate. That would be difficult if, without the graph, if I just said, hey, look at this real quick. What's the biggest number you ever get out of this? That'd be difficult to just look at that and guess it, right? But with the graph, we know it's -7. Is there any number that I could ever plug into this, that I could plug in and get the number 2 to come out? No, you can say that with certainty. 2 is up here, isn't it? It's never coming out of there. Make sense? So there's actually a lot of information we know about this graph, about this function by its graph. You can plug any number you want in. You're never going to get a positive number out of this. It's always going to be a negative answer, right? Always. All right. I think we are ready to talk about those falling bodies, those falling objects. Do y'all think 2 of those was good enough to get us set up for the applications? Okay. Okay. Falling objects on Earth without air. So I put this formula up here earlier. D of t, so that's like f of x. Okay, that's the same thing. D of t equals negative 16 t squared plus v naught t plus d naught. So now I will explain what everything here represents. Okay, d naught, or d sub 0, is the starting height of the object in feet. Okay, so this is measured in feet. V naught is the starting velocity of object in feet per second. So this goes back to, remember, I'm dropping the 2 pins, or I could like push one down or like throw one up, right? And it's going to land at a different time. Another thing that you can think of is, imagine that you're standing on a helicopter, right? And you're going to jump out of the helicopter, all right? I don't know why, but you're going to jump out of the helicopter. So if that helicopter is just sitting there hovering and you jump out, just step off, then this V naught is going to be 0, because you're just going to step off and start falling. But what if that helicopter was actually rising as you step off? So it's going up. Then what's going to happen is, as you step off, you're actually going to go up just a little bit before you go down, because you actually have some speed vertically. All right, so if that starting velocity is going up, it's going to be a positive number. I told you this earlier, and if it's down, it's negative. So I need to state that here. V naught will be positive if the speed is up, and V naught will be negative if speed is down. All right, what else do we have in this that I need to describe? T. What's T? T is the time measured in seconds. For those of you who've done some physics in the past, you may remember that the acceleration of gravity is negative 9.8 meters per second, if you've ever heard that. This right here I told you is gravity. The reason it's not negative 9.8 meters per second is because we're in feet per second, not meters per second. And that's why the formula looks a little different. If we went to meters per second, this would change. All right, so T is time in seconds. So think of it this way. What if we're, again, going to step off the helicopter, right? We're just going to step out off the edge. Right as I start to do it, that's time equals 0, right? Time is 0. So if you plugged in 0 here and here for t, what would you get? You would get this number, right? And that's your starting height. So at time equals 0, that's where you're starting. Then after that, as the time changes, then your height is going to, do something, right? And the last thing here is what d of t is, the left side. D of t is exactly the height of object at t seconds. So again, if you plug 0 into this for t, then d of 0 would be your starting height. D of 1 would be how high the object is after 1 second. D of 2 would be how high the object is after 2 seconds, and so on and so forth, right? Okay. Now, can you tell me right now, if I were to ask you to graph one of these, what it would look like? It would open down. We know that for sure, right? It would open down? Okay, so I know that when you draw this, it's going to look like this. It's going to be down, right? So it could look like this. Oops. That's one possibility. Now, why am I not continuing my graph this way? This is t, right? T is like the x was, and t for us is time. We are not going to have anything, negative time will not make sense to us here. So our graph will always just start at the y-intercept, and then it will end where? At some intercept here, right? And that's when you would hit the ground, right? Okay, so it could look like that. Here's another possibility. That could actually be your vertex, right? So you notice here, this point was a y-intercept, but it wasn't your vertex. Here, it is your vertex. Do you see that? Well, you're assuming it is. You're assuming it goes like that. You could even have a third possibility where the parabola actually has a vertex back here. You see that? Like your vertex is actually back here, but because that's negative time, you're picking up at the y-intercept but not at the vertex. Here you're picking up at the vertex. This would be an example of an object that is thrown up. So if you throw an object up into the air, take that pin, throw it up into the air, it's going to go up a little bit first, then come down, right? This is an example of something where you just step off, right? You just step off. You're at the vertex, right? When you start, you're at the highest point. And then this one right here is a little confusing, but this is what would happen if you throw something down. So I'll give you all three of those visually. Okay? This right here is this situation, right? That's that situation. This one here is this situation, right? And this one here is that situation. Understand? Up, throw it with the velocity upward, no velocity, or velocity downward. Okay. All right, that's everything we need. Why don't we take a break and we'll come back and we'll do an example. Sound good? 12:15, we'll come back at 12:25. Sucks? What? What happened?
Because I missed the last class.
Oh. Oh, and the video wasn't up either. Yeah, sorry. You'll get caught up. You'll get up to speed. All we did last time was some factoring and using quadratic formula. So.
Like, I remember, once I see it, it'll.
Okay. Good, good. Let's go. So this first problem is kind of a boring problem. Someone standing on a bridge throwing a rock. The next one, I promise, will at least be a little more interesting. So this person's going to throw a rock. This is a 50-foot bridge they're standing on. They're going to throw this rock up, and it's going to come back down under the influence of gravity, right? But they're going to throw it up. Now, one thing that's interesting, I think is very interesting, is the fact that if this person threw this rock straight up, or if this person threw this rock out and like over, right? As long as it has the same upward velocity, the rock would actually hit the ground at the same time, regardless. Now, this is very interesting because here's a way I can try and explain what I'm talking about. If I take these two pins and let's say I drop one of them, but the other one I throw horizontally out, which one is going to hit the ground first? So I'm just going to drop this one. I'm going to throw that one out to the side. Try and release them at the same time here. See if I can do these. It's good enough. So what is your guess as to which one would hit the ground first? They should hit at the exact same time. Think about that. That if I drop this one or throw this one out to the side, they will both hit the ground exactly at the same moment. So this horizontal movement does not have any impact on its downward movement. That means if I take a gun and I shoot a bullet out of the gun and I drop a bullet right next to the gun at the same time, the bullets hit the ground at the same time. That's an interesting idea. You know, like if I'm shooting a gun at a target, there's my gun. Again, artistic abilities are top notch here. Okay, so if I'm shooting at a target here like this, then can I aim directly horizontal? Can I aim flat exactly at the target and hope to hit it? No, this bullet is going to fall like a parabola. It is going to have some parabolic path. So that means I would have to aim up a little bit, wouldn't I, to make it hit that? Now, one thing I could do is to make it so I don't have to like aim way up here, is I could increase the speed of the bullet. So if I increase the speed of the bullet, then it's going to go from here to, let's say, here. If that takes 1 second, it's going to drop quite a bit, right? But what if it gets from here to way out here in 1 second? It's going to drop the same amount, right? So it won't drop as much back here. And this is what snipers and stuff in the military have to deal with, is, you know, trying to figure out the velocity of their bullet, and then they take into account gravity and wind and humidity and all these different factors and try and predict where their bullet's going to hit out there. It's very complicated, but another kind of amazing fact is, what if I was able to fire a bullet so fast that as it started to drop, the earth actually started to curve away from the bullet? Think about that. I'm standing here on the earth. I'm very big. I shoot a bullet out, right? Straight out. It's going so fast that as it starts to drop, the earth actually is curving away. Then what's going to happen? It's just going to go and keep trying to fall towards the earth, and the earth keeps curving away from it and keeps trying to fall, keeps curving, and then what do you get? You get orbit. Yeah, you shoot yourself in the back of the head. You get orbit. This is what our satellites are doing up in space, right? We send them out, we get them to a certain speed, a certain height, we cut the engines off, and they start to fall towards the earth starts to curve away, and they just sit there in this perpetual loop around the earth. That's what the moon's doing to us. It's what we're doing to the sun, basically. We're just constantly falling. But yeah, it's kind of interesting. That's what satellites are. Okay, whoa, back here. So we throw this ball up, comes back down. The question is, what's the maximum height of the rock? It's a rock, not a ball, sorry. What's the maximum height of the rock? When does it reach its maximum height, and when does it hit the ground? Right? So let's try and interpret what these questions are asking us. Like, what is part A really asking us for here? The vertex, right? But which part of the vertex? Remember, the vertex is actually the point HK, right? So we know that this parabola opens down. Why? Because, well, this is an object falling in Earth, and the formula is negative 16t squared. That negative 16 tells us it opens down. So when it's saying what is the maximum height of the rock, vertex is slightly right, but the vertex is a point, so it's the K. The K is the actual height, isn't it? So what we're really looking for here is the K from the vertex. What is part B asking you for? When does it reach its maximum height? When is time, isn't it? And time on our graph is left and right. And that would correspond to this, wouldn't it? And that would be your H. So that's asking for the H from the vertex. And then what is part C asking for? When it hits the ground, right? When it hits the ground. So you want to know this left and right, which would be the X-intercept, wouldn't it? That make sense? So I'm going to put here X-intercept. Although technically they're not really X-intercepts in this problem because we're using the variable t. So you could say that these are the t-intercepts, but I'm just going to say X-intercepts because that's what we've been doing. Make sense? So on a test, I will ask you these questions. Guaranteed, there will be a word problem like this on a test. I may not ask you these in this order. Okay, so don't just be like, oh, when I see that word problem, I'm just going to get K, H, and X-intercepts. I may switch these so that you have to know which one it is, all right? So what is the maximum height? You want to know the height, that's K, that's the up and down. When, that's time, that's left and right. When, that's time, that's left and right. So, yeah. All right, let's do that. I think for this, we can do this. We don't need to graph it, right? It's not asking us to graph this. So we just need two things for this. We need the vertex and we need the X-intercepts. But do we even have a function? Do we have a function? No one gave us a function, right? So we have to go back to the formula, which I would provide you on a test, all right, or I would allow you to have on a formula sheet. We have to go back to this generic formula, and we have to fill in the blanks first before we can use it. So what do we know? What's the 50 in here? D naught. This is the initial height, right? That's the height the rock starts at, 50-foot bridge. Now, if you're standing on a 50-foot bridge and you have a rock here, of course it's not going to be 50 because it depends on where you're holding it. But let's just say 50, all right? Okay, so 50-foot bridge, this is going to be 50. And then you're throwing this rock upward with a velocity of 22 feet per second, right? Upward velocity is your V naught, right? And since it's up, I'm going to use positive or negative? Positive. So I'm going to replace V naught with positive 22. I'm just stressing that it's positive, right? If we throw the rock down, it's going to be negative 22. All right, so our formula that we'll be using for this problem then becomes negative 16t squared plus 22t plus 50. Okay, that is because physics is the way it is, and because we're neglecting air, it doesn't matter if this is a rock or a paper clip or a feather. With no air, they're all going to follow this formula, right? So now I just need to figure out what my vertex is and figure out my X-intercepts, and I'm done. So let's get the vertex. Let's get the vertex. How do we calculate H? Negative b over 2a. So for us, that's negative 22 over 2 times negative 16. Yes? Negative 22, we take the opposite of the number in front of t and divide it by 2 times a. A is negative 16. And we should get a decimal here. Point what? What is it, 0.68? Okay, let's go with 0.68. That's fine. So do you agree that we have an answer to one of the problems already? We actually have the answer to part B. It's H. Okay, now let's get K. So how do you get K? You're going to plug that into here, right? So watch the way I write this. I'm going to write D of 0.68. Notice I'm not writing F of 0.68 because the function is called D, not F. So I'm plugging in 0.68 into here. So this is going to be negative 16 times 0.68. We're going to square that, plus 22 times 0.68. Yes, you're going to have to use a calculator, plus 50. And hopefully you can grind this out. I'll do this piece by piece. This first piece here should be negative 7 I'm going to go with 4. I'm going to round that a little bit. Plus 14.96 plus 50. I'm getting 57.56. So let's go ahead and answer part A and B. Right? What is the answer to part A? What's the maximum height of the rock? 57.56 feet. Right? Don't forget you need to put the unit there because you're answering like a word problem, right? 57.56 feet. Started out at 50 feet. You threw it up with 22 feet per second. Gravity took over. It only got up to 57.56 feet, and then it started coming back down. Now, how long did it take to reach that height, that maximum height? So when you threw it, left your hand, clock started going up. How long did it take before it reached that maximum height? 0.68 seconds, right? Half a second almost. A little bit more, 0.68 seconds. See, the important thing now is that we're asking when it hits the ground, right? So if it took 0.68 seconds to get to its maximum, you're not just going to double that to get to the bottom, because if you double that, where would you be? If you double that time, it goes up, takes 0.68 seconds. 0.68 seconds later, it's going to be where? Right where you started from. And then it's got to drop to 50 feet, but it keeps speeding up as it goes. So we have to actually find the X-intercepts. There's no way around it. So we're on part C now. Let's find the X-intercepts. And to do that, all we have to do is take the equation that we have over there and set it to 0. Negative 16t squared plus 22t plus 50. And I made this problem up out of my head, so I can almost guarantee you that's not going to factor. And that means you're going to have to use a quadratic formula. So my answers are t equals negative b plus or minus the square root b squared. We have to square 22, just to be sure, 484, minus 4 times a, which is negative 16, times c, which is 50, all over 2 times negative 16. This should turn out to be a plus in here, because you have a minus and a minus can be plus. So I'm going to do 4 times 16 times 50. And then add that to 484. So negative 22. Also, notice I use t instead of x, right? Because I'm solving for t, not x. So plus or minus square root. When I put all that together, I'm getting 3684. Anyone else under there? All over negative 32. Then I have to take the square root of that. So negative 22 plus or minus 60. Let's go 60.7 over negative 32. Now, I'll let you take it the rest of the way here, but you should get two answers. One of them is negative 1.2, and the other one somebody else can confirm this with me, 2.58, 2.6? Anyone else get these or something close to? Am I the only one? Yes? Okay. So, what's our answer? 2.6 seconds is how long it takes to hit the ground. When does it hit the ground? 2.6 seconds later. So we throw the ball up, or rock up, with a certain amount of speed. Takes 0.68 seconds to reach its maximum height of 57.56, and then falls to the ground. Total time from when it left my hand, up, back down, hit the ground, took 2.6 seconds. Now, why did I not consider the negative 1.2? It's negative, right? See, the math, right? In the mathematics of the problem, it's giving us a parabola. Sorry, it looks more like this. We found that vertex, right? We found one of those X-intercepts. Mathematically, there's another X-intercept back there. There's another one, but it doesn't make sense to look at the negative time. All right? What do y'all think about that? Think you can handle that? Questions, comments, concerns, complaints? All right. So this next one, let me kind of give you some motivation here. I'm not trying to depress anybody today or make anyone upset. All right, it's not my goal, but back when I was teaching this class many years ago, it was after 9/11, right? When the towers were hit, right? Like a year later, I was doing an application problem in a college algebra textbook. And in the textbook, it was talking about dropping a rock off of the Twin Towers, off of one of the Twin Towers. This is like a year after the towers had fallen. And so we were all sitting there like, kind of still distraught from it all and everything. And, but we still did the problem. And so I always like to still cover this problem but I've kind of adapted it a little bit. I don't know, people seem to pay a little more attention whenever I talk about something that's like, I don't know. You know what I'm saying? If I talk about a rock falling off a building, people are like, okay, a rock falling off a building. When I talk about people jumping off a building, choosing death by fire or death by jumping, people pay more attention for some reason. So, I mean, right? Okay, so look. On that fateful day, the Twin Towers stood at approximately 1,300 feet. No, that's way wrong. Hold on. 2,300 feet. Is that right? I better double check this. No, I was wrong. I was right the first time. 1,300. Yeah, it was like 2,300. That's like half a mile. That's okay. 1,300 feet. All right, 1,300 feet was the height of the buildings. Now, the planes, one of the planes in one of the towers hit, at lower floors. I forget what floor it was, 80 or something? Like 90th or something like that. And the people trapped above, at some point had to make a decision as to whether to jump out of a window or to stay and either burn to death or inhale enough smoke where they are overcome, right? And some people chose to go off the edge, right? So let's approximate that height was 1,000 feet. And trust me, I'm not trying to make light of this at all, okay? I'm not trying to make light of it. It's just that that's a long fall, right? That's a long fall. And if you actually, if you go and watch the video of the towers actually coming down, have you ever noticed it seems to take quite a long time, right? We'll get to that point in a second. But what I want to know right now is how long this fall would have taken, right? So if this is like making you too disturbed, then just imagine a rock falling from 1,000 feet, okay? But what is the time it would take to fall this distance of 1,000 feet? So could you do it with what we've learned today? All right, so this is a falling object on Earth. We're going to neglect air. We're going to neglect it, although it did play a role. All right, so what we have is this formula. D of t is negative 16 t squared plus v naught t plus d naught, right? So what do we know here? D naught is what? 1,000 feet, right? This is not quite the top of the building. It's, you know, out one of the floors towards the top. So each floor is about 20 feet. So we're assuming that, you know, they're down a little bit here. And then what about V naught? What about this one?
Gravity, 120.
Well, this is going to account for gravity. This is your initial velocity. Think back at the marker. Okay, is it being thrown down, thrown up, or is it just dropped? We're just going to assume that it's just, you know, the person just steps out, right? It's not some big leap up into the air first. It's just falling straight out, right? Let's assume that. So what would V naught be? 0, okay? That's all you need. You've got everything. So the formula becomes negative 16 t squared plus 1,000, right? This is d of t. Now, my question is, how long did it take before they hit the ground? So what am I asking for? The X-Intercepts, right? Which means you need to set that equal to 0. Set that equal to 0. So if I set this equal to 0, negative 16 t squared plus 1,000 equals 0, we have a quadratic form. I mean, we have a quadratic equation, but this is a little different than any of the equations we've looked at so far. Only because A, B, and C are a little bit weird here. What's A for us in this formula? Negative 16. And then what's B? B is 0, right? Because there is no t term in the middle. And then what's C? 1,000. When this happens, you can still use the quadratic formula. You can still use it. All right? There's nothing wrong with going through and using quadratic formula here. But there's a faster way. And the faster way is to take this and move it to the other side of the equation. So when you do that, it becomes positive, right? So you're adding that to both sides. So you get 1,000 equals 16t squared. Are y'all with me on that? And then divide both sides by 16. And you get, so I'm taking this divided by 16, taking that divided by 16, and what I'm getting is 62.5 is t squared. And now you just take the square root on both sides. So if I take the square root on this side and take the square root on this side, you have to keep in mind that when you take the square root of a number, you have to do plus or minus. This isn't going to matter to us because it's time, and time won't be negative. But let's see, square root is 62.5. I'm getting 7.9. So t is 7.9 seconds. So an object in free fall from 1,000 feet will take 7.9 seconds to reach the ground. It's a long time.